Okay, Kiboko. We are team number 3, and we are going to talk about our pendulum, which objective was to build a model which had its axis anywhere but at the end of the piece. And with that, we had to calculate the moment of inertia, the angular frequency, the period, and the center of mass.
Now the process of making this pendular system was by putting two poles that hold a metal ball. This was using cardboard. This is a metal ball where the pendular system is put in this axis, and this was a PVC pipe, and in the end this is a plastic ball.
In order to measure the experimental period, the process is we need to pull the ball and then let it go, count the time, and then stop it from where it was dropped.
To get the error percentage of the period, you need to get the theoretic period and the experimental period between the theoretic period times the 100 to get the percentage. And the percentage we get is 8.2.
The pendulum has been used by scientists in 1850 when Foucault used it to prove the rotation of the Earth. Like, he made a build model, and then they started to see the rotation, and that's how they saw how the Earth moved. And also a very clear example is the clock, the long case clocks that have a pendulum inside that with a period of 2 seconds, 1 second from one side to another, and that's really useful because the time has to be.
Okay, in order to get the initial angular frequency, we have this formula in which we substitute our previous data. Then we have this final number. We have 7.7, and the units are in radians per second. Then we have the formula for the period, which is 2p over the initial angular velocity, and then we have these number, and the units are in seconds. And then for the frequency, we have that is 1 over the the period, and that's where we get the 1.23.
In our free body diagram, we have the weight that is on the center of mass of both the sphere and the bar. The bar has a center of mass and the sphere has another center of mass. And we have the acceleration that side, but this is not a force. Then to see what is the inertia, we need to take the inertia of the bar plus the inertia of the sphere. The inertia of the bar is this because the formula plus L, that is the distance of the center of mass to the axis, square plus the mass. And the sphere is this part because the formula plus the mass of the sphere times L plus the radio of the sphere square. Then we did the math, and this is the result of the inertia. Now to take the center of mass, we have the sum of masses plus distance over the sum of the masses. Is the mass of the sphere and this is the result in meters, and in centimeters is 19.2.
The reason for why we have the this percentage of error is because the human reaction is not as exact, and maybe because some decimals were not taken into account.
Conclusion. We accomplish our objective by calculating all the unknowns on the pendulum system. We can conclude that the process of solving is different depending on the location of the pivot. Formulas of the inertia also change from the structure to structure because, as we experimented, an object with higher mass has more inertia than a lower mass object, as it's needed a bigger force to move a heavy body. Thank you.